So, hey everyone, we are Group 2, and the Group 2 involves myself, Harish Rajvel, and Abhishek, Ilakya, and Vidyadhar. So, we will be talking on the topic mechanics of fracture and failure in graphene. So, before proceeding, we'll see what basically graphene is. Graphene is a two-dimensional nanomaterial that is basically a single layer of carbon atom whose thickness is primarily negligible. So, that's why it's called two-dimensional, and it has X signal structure similar to graphite, and it has great properties such as high thermal and electrical conductivity to go along with lightweight and incredibly durable and with high strength. So right now, graphene is primarily used in electronic devices due to its high thermal and electrical conductivity, but it's under research to expand the application into mechanical structures such as aeroplane wings and aerospace industry, etc. And we've gone through multiple papers understanding the graphene mechanics and its properties, etc., to have a better idea of what graphene is. So in this paper, we'll go through the different loads that's been put into graphene and see the experimental results. And basically, under tensile strength, graphene experiences a large deformation along the stress orientation. And this deformation is primarily on PW1 and PW2 kind of deformation that involves change in bond angles and bond length, respectively. And then graphene exhibits as a a particular property called as negative Poisson ratio. That's basically when you have a tensile load, the lateral distance increases rather than decreasing. And this is applicable only in graphene. And this paper also involves molecular dynamic simulation through which, we were able to find the Young's modulus, which is then came out to be 340 for monolayer. And it also considers loading effects of buckling. And in the buckling effect, we can see the sudden sideways deflection of the central part of a graphene sheet. And also fracture toughness and other kinds of tests were done through the microscale tensile testing here. And this material, all these tests were done for both monolayer and bilayer material, and distinctively two different kind of results were observed, suggesting different properties for different layers of graphene sheets. And with the simulation, we were able to find the shear strength to be around zero point 0.2 terapascal, which is pretty high. Going on to the second paper, this paper primarily involves in factors such as hierarchical structures, impact of interlayer and intralayer processes to find the best method to synthesize graphene effectively. And most of these calculations were done in a continuum model, and most of the factors such as interlayer crosslinks were involved, such as water layers, epoxy group, hydrogen bond, etc. And in the graph, you could see the all the bonds which are previously mentioned against the shear strength calculated against each bond to find the exact mechanical behavior. And these are images of all the bonds that's been mentioned. And the shear strength through the formulation and experimental design are found out to be 367 megapascal, which is pretty high than the tensile strength of most of the hard steel material. And this was one of the way this was done was using the deformable tension shear model, which was primarily inspired by the hierarchical, structure of the biomaterial. And when this was implemented at different layers of the graphene, it had different effects as well. So it also like this paper, apart from the interlayer crosslinks that were mentioned earlier, it also covers intralayer crosslinks. And with the experimental setup, we were able to bring up formulation to find the tensile strength and the compressive strength. And with all these experimental results, we were able to find the three, graphene synthesis method. So basically, in order to increase the overall resistance, we can maintain the layer by layer hierarchy, and to get the optimum stiffness of a graphene sheet, the graphene sheet should exceed 23 uh, nanometer. And for increasing the overall structure, it's better to improve the interlayer connections.
I am Vidyadhar. The next article that we reviewed was fracture strength and fracture toughness of graphene using MD simulations. Objective here is to address the validity of Griffith's theory and AWV issue used for predicting the graphene's fracture properties. Griffith's theory, the theory of linear elastic fracture mechanics, proposed in the year 1921. This theory, in fact, revolutionized the researchers' understanding of material failure due to cracks and fractures. The theory is based on the concept of using energy-based approach to predict fracture in the material. Till date, the theory has applications in various fields, including nanoengineering, earthquake engineering, biomechanics, and many more. In terms of methodology, the research team performed MD simulations on hexagonal lattice structure of a monolayer graphene sheet. Molecular dynamic simulation method is used to study the properties of materials and also to analyze how molecules move at atomistic levels. To do more MD simulation, there are three important steps. First one is to create initial state of our system, later introduce the interaction potential between particles, and finally predict how particles move by integrating Newton's equations of motion. There are several MD simulation packages. The commonly used packages are LAMPS and GROMAX. The image of MD simulation done using LAMPS is shown in figure 1. Moving on to research findings, the influence of AW ratio. The team systematically investigated the influence of this ratio on fracture toughness, where here A represents the crack length and W represents the width of the graphene sheet. During this study, the team defined the lower bound value for AW ratio beyond which the Young's modulus starts to decrease with increasing crack length. The fracture toughness initially increases with increasing AW ratio. It reaches a peak value, and beyond this peak value, it decreases. Through their results, the team recommended the AW ratio in the range of 0.15 to 0.45 to have better predictions on graphene's fracture toughness. And moving on, the next article we reviewed was a deep learning model to predict fracture mechanisms of graphene. The objective here is to understand the fracture mechanisms in graphene and also to overcome the computational limitations associated with MD simulations. Generally, MD simulations are expensive and time consuming especially when the number of molecules are more. In terms of methodology, the team applied the deep learning approach to predict nanoscopic fracture mechanisms. The study was focused on a real technologically relevant material, graphene, with higher chemical complexity and covalent bond breaking at its core. This is an ideal test case for this deep learning approach. A convolutional, long, short-term memory-based deep learning model was used. This model was designed to tease out the spatio-temporal relationships underlying fracture propagation, and the machine learning model was trained using the datasets generated by the MD simulations. Moving on to research findings, the deep learning uh, model successfully predicted nanoscopic fracture mechanisms in graphene. It focused on crack instabilities and branching patterns as a function of crystal orientation. The model demonstrated accuracy in capturing graphene fracture behavior, including the fractal dimensions shown in figure 2. In terms of discussion, by overcoming the computational limitations, this approach enables large scale predictions. The results of the research validate the potential of deep learning in material science research, and this opens up the possibilities of studying other 2D materials beyond graphene. Moving on to significance, the model demonstrated excellent predictive power across various loading conditions and material orientations. The researchers now could possibly significantly reduce the computational burden associated with traditional fracture prediction methods.
This is Ilakya. We have done the literature review of fatigue of graphene and for graphene composites. The objective of the first paper is to investigate fatigue behavior and damage mechanism of 2D materials such as graphene and graphene oxide, to experimental testing and molecular dynamics simulation to evaluate the long-term reliability and potential application. The methodology involves preparing monolayer and a few layer graphene oxide films, conducting fatigue testing and monitoring the force signals. Experimental testing captures fatigue behavior where simulation provides the insights. The study combines the experimental and computational approach to understand fatigue mechanism in 2D materials. The key findings are the monolayer graphene experiences global catastrophic fatigue failure, while graphene oxide demonstrates a local progressive damage mechanism. Molecular dynamics reveal stress bond near defective sites to show fatigue failure. The research findings reveal that the monolayer graphene exhibits a fatigue life exceeding 10 to the power 9 cycle with global catastrophic failure, which graphene oxide shows global progressive fatigue damage mechanism. Molecular dynamics simulation highlights stress-mediated bond reconfigurations in graphene and progressive damage in graphene oxide. Going to the next slide, coming to the scope of development, understanding the fatigue behavior of 2D materials provides insight into their long-term reliability under cyclic stress condition. The study demonstrated that even a small amount of graphene can improve the fatigue life of polymer-based composites. The study serves as a starting point for further research on fatigue behavior of 2D materials to develop their new testing methods and to investigate the fatigue properties of other 2D materials beyond graphene. Going on to the next slide. you're going to see about the second paper, fatigue behavior of graphene composite. The objective of this is to investigate the fatigue behavior of graphene composites and explore their potential for enhancing the durability through advanced material testing and analysis. The methodology shows that the graphene composites will be fabricated using various techniques followed by fatigue testing under controlled conditions to look at their mechanical performance. Fatigue life, crack initiation, and propagation will be analyzed using advanced testing equipment. Data from them will be collected, analyzed, and compared to the existing literature to evaluate the impact of graphene fillers on the fatigue strength of composite materials. The key factors influencing the fatigue behavior of graphene composites include the type and the concentration of graphene fillers, dispersion with the matrix, interfacial interaction, toughening mechanism, crack propagation pathway, and the presence of particles are the key factors. And coming on to the research finding, these indicate the graphene fillers in composites can be fatigue performance by enhancing the crack resistance and delaying crack propagation. Different graphene concentration and shape influence fatigue resistance mechanisms, such as crack bridging and void growth. Additionally, graphene coatings on materials like aerogels enhance fatigue strength and shape recovery. However, the size and orientation of graphene particles can affect the crack propagation, highlighting the complexity of fatigue behavior in graphene composites. The scope of development includes further research on fatigue behavior of composite materials filled with functionalized graphene to understand the benefits compared to neat graphene. Exploration of graphene fillers in composite sandwich structures to enhance fatigue strength. Continued study of interface interaction between graphene and the matrix to optimize composition performance. Going to the next slide.
Hi, this is Abhishek. This paper is about the elastic straining of freestanding monolayer graphene. The researchers focused on studying the mechanical properties and fracture behavior of monolayer graphene. They used a chemical vapor deposition process to synthesize monolayer graphene and transferred it to a tensile testing setup using PMMA wafers. And tensile tests were conducted on the suspended graphene, visualizing the test under scanning electron microscope using a PI85 indenter. They also conducted molecular dynamic simulations to verify the experimental findings and investigate the crack propagation in graphene. The key findings of the research includes monolayer graphene exhibiting elastic response, demonstrating high stretchability, and the tensile strength of monolayer graphene was measured to be 50 to 60 gigapascals, and the sample-wide strain was measured to be approximately 6%. And they also found that the edge defects affect the mechanical properties of graphene. Moving on to the research findings, the research demonstrated that in situ quantitative tensile testing of suspended graphene is feasible, and the measured tensile strength of monolayer graphene exceeds the ideal strength of graphene, indicating that the edge defects affect the mechanical properties of graphene. And the fracture initiation majorly occurs at the edge defects, and it is determined by the lattice orientation and mechanical anisotropy. The scope of development in this field includes sample preparation process that could be optimized to get better results, and the tensile testing methods could be improved continuously to enable a more accurate characterization of graphene's properties. And the future research could also focus on exploring other strain effects in graphene. The next paper is about in situ fracture toughness measurement of multilayer graphene. The objective is to calculate the fracture toughness of multilayer graphenes, and the methodology they use is chemical vapor deposition process to grow different numbers of layers of graphene on copper foil. Graphene is patterned to fit the area of MEM stage, and the graphene is patterned to avoid unnecessary graphene covering the MEM stage, which could hinder some imaging. And graphene was transferred onto the MEM stage using a PMMA wafer. And the key findings are that crack propagation in monolayer graphene propagates in straight lines, whereas the propagation in multilayer graphene is along the grain boundaries. As the number of layers of graphene increases, the fracture toughness also increases. And the results suggest that multilayer graphene has higher fracture toughness than monolayer graphene. Moving on to the research findings, the numbers of layers of graphene used for the study were 5, 7, and 12, and the fracture toughness was measured to be 22, 71.3, and 145 joules per meter square, respectively. And the grain boundaries play an important role in the fracture behavior of graphene. The scope of development in this field includes crack propagation in multilayer graphene that could be studied using molecular dynamic simulations. And the application of multilayer graphene could be explored in the future. The research papers we reviewed are included in the reference page. Thank you.